Welcome to the chapter overview of chapter number 1, Chemical Reactions, where we decode chemical reactions and equations. These reactions are the fundamental processes that govern the natural world around us, from the smallest atoms to large-scale transformations. Matter is in constant translation. A chemical reaction occurs whenever the nature and identity of a substance change. These fundamental processes drive daily life, including oxidation, acidification, fermentation, and even respiration. We cannot directly see atoms rearrange. Instead, we look for macroscopic evidence, or physical signatures, that indicate a chemical translation. These include a shift in state, color, the evolution of gas, or a thermal shift. Describing chemical reactions in natural language is imprecise. Science uses an exact, symbolic syntax to show the transformation of reactants into products. This system progresses from a simple sentence to a word equation, and finally, to a skeletal equation using chemical symbols. A key principle is the law of conservation. Mass can neither be created nor destroyed. The total mass of elements in the reactants must exactly equal the total mass in the products. A skeletal equation often breaks this law, which is why balancing is necessary. Balancing a chemical equation requires equalizing atoms on both sides without altering the fundamental formulas. The hit-and-trial algorithm involves 3 steps. Isolate the unbalanced equation, iterate by adding coefficients, and verify the resulting balance. A complete chemical equation acts as a standalone data packet. It details not only the mass, but also the precise physical states of reactants and products, and the environmental triggers required for the transformation. All chemical reactions are categorized into foundational patterns based on how atoms break and form bonds. These include combination, decomposition, displacement, and double displacement reactions, each with a unique, quote, logic code and real-world signature. Combination reactions, often called the exothermic engine, occur when 2 or more substances fuse to form a single product. The creation of new bonds in this process often releases a massive amount of energy into the environment as heat. Decomposition reactions, or the endothermic input, fracture a single reactant into simpler products. This requires a continuous input of energy, absorbed from the environment in the form of heat, light, or electricity. The flow of heat dictates the system's energy exchange. Exothermic reactions, like the burning of natural gas, result in energy flowing out of the system. Endothermic reactions, such as the heating of limestone, result in energy flowing into the system. In a displacement reaction, a highly reactive element physically displaces a less reactive element from its compound. This demonstrates a clear hierarchy of chemical force among elements. Double displacement reactions occur when 2 aqueous solutions mutually exchange ion partners. This often results in the formation of an entirely new insoluble compound known as a precipitate, which falls out of the solution. Oxidation and reduction, or redox, are 2 sides of the same coin. If one reactant is oxidized, the other is simultaneously reduced. Oxidation involves the gain of oxygen or loss of hydrogen, while reduction is the opposite. The language of nature is a beautifully symmetric and interconnected system of transformations. Combination and decomposition are exact reverses, and oxidation and reduction occur simultaneously in a redox reaction, demonstrating fundamental chemical balance. Understanding chemistry allows us to engineer interventions against degradation. This includes preventing corrosion, where moisture catalyzes the oxidation of iron, and blocking rancidity, the oxidation of fats and oils in food packaging. Thank you for studying with us. Meet you in the next chapter overview.